Hi friends, welcome back to Acharya Gurukulam. Today's topic is the deflection of a cantilever beam using various methods. There are various methods to find out the deflection of a beam. In this video, I'm going to explain how to calculate the deflection of a cantilever beam using double integration method, moment area method, conjugate beam method, and energy methods. First of all, we would like to understand the differences between displacement, deflection, and deformation. Displacement is the distance from which one node or element moved from its original location. It can be measured in terms of distances or rotations. Deflection. It is the distance that an object bends, twists from its original position. Deformation. It is the actual distortion that occurs to a structural member. We most commonly discuss elastic and plastic deformations in our analysis. Elastic deformations are those deformations that when the loading is removed, it will return to the original undeflected shape. Whereas in plastic deformations, these deformations are those that will remain even after the loading is removed. Now we'll discuss about how to calculate the slope and deflection using a double integration method. Let us consider a cantilever beam having a length L subjected to a uniformly varying load with an intensity Q naught at point A and determine the slope at point B and deflection at point B. Generally, in most of the textbooks, the problems are given for a cantilever beam subjected to point load and a uniformly distributed load. But very rarely we can see the problems like cantilever beam subjected to uniformly varying load. First, we'll calculate the intensity of the distributed load at a distance x. Now, how to measure the distance x? So, the distance x is measured from point A. So, you can take any distance from point A to point B is the distance x. So, if the x is equal to 0, that means at point A, the x is equal to 0. At point B, x is equal to n. Now, from that, using similar triangle principle, we get Q is equal to Q naught into L minus x by L. So, how we get this? You take a point you take a distance x somewhere here and using similar triangle principle, that is q naught divided by L is equal to, let us take this is a q divided by L minus x. So if this is the distance L and this distance is x and the remaining distance is L minus x, so q naught divided by L is equal to q divided by L minus x. Then we'll obtain q is equal to q naught into L minus x by L. Now that y is the deflection, and first differentiation of the deflection is slope, then d square y by dx square is the moment, d cube y by dx cube is the shear force, and d power 4 divided by dx to the power of 4 is the intensity of the loading. This is very, very important. The fourth order differential equation becomes ei into d to the power of 4 y divided by dx to the power of 4 is equal to the intensity of the loading. So d power 4 divided by dx to the power of 4 is equal to q. So which is equal to q naught into L minus x by L. Now, to obtain the shear force, integrating these terms once, then di into dqy by dx cube is equal to q naught divided by 2l into L minus x, uh, L minus x square divided by 2. So for this term L minus x, so if you take the integration, L minus x square divided by 2 plus C1. Apply the boundary conditions to obtain the constants. So what are the boundary conditions? If you see, d cube y divided by dx cube becomes 0 at x is equal to L. Now, if you go to the diagram, so at this point, the shear force is equal to 0. So that means the d cube y divided by dx cube is equal to 0. So that means this term will become 0 and calculate C1. So when you substitute x is equal to L in this equation, x is equal to L. So L minus L is equal to 0 and d cube y divided by dx cube is equal to 0. Then C1 is equal to 0. And substitute the constant. So if C1 is equal to 0, then the shear force is equal to EI into d cube y divided by dx cube is equal to Q naught divided by 2L into L minus x whole square. So this is what is the shear force for a cantilever beam subjected to uniformly varying load at any point x. Now let us discuss about the bending moment. So for obtaining the bending moment, you take one more integration, that is EI into d square by dx square. EI into d square by dx square is equal to minus q naught divided by 6L into L minus x cube whole cube plus C2. So q naught divided by 2L into L minus x whole square is the shear force. So q naught divided by 2L, L minus x, for this L minus x square, you have to take the integration. So L minus x whole square, the integration is L minus x whole cube divided by 3. 3 into 2 is equal to 6. So that's why the bending moment is equal to EA into d square y by dx square is equal to minus q naught divided by 6L into L minus whole cube plus C2. So in case of bending moment, the boundary conditions are d square y by dx square is equal to 0 at the free end. So if you see the diagram, so at this point, the bending moment is equal to 0. So that is d square by dx square is equal to 0 at the free end of the cantilever beam. Apply the boundary conditions and obtain CT. So then CT is equal to 0. So substitute the constant in this equation, then we'll obtain moment. So that is EA into d square by dx square is equal to minus q naught divided by 6L into L minus x whole cube. Now, the third and fourth integrations yields to the slope and deflection of the beam. So that is EI into dy by dx. So as we already discussed, dy by dx is the slope of the beam is equal to Q naught divided by 24L into L minus x whole to the power of 4 plus C3. So the third and fourth integrations yields to the slope and deflection of the beam. So that means whatever the moment equation that we have, that is EA into d square y by dx square. If you take the further integration, then EA into dy by dx, which is equal to Q naught into 24L into L minus x whole to the power of 4 plus C3. So how we obtain this equation means, so similar to the shear force and bending moments as I explained in the earlier case, then again you have to take one more integration, that is EA into y to obtain the deflection is equal to minus q naught into 120L into L minus x whole to the power of 5 plus C3x plus C4. So after applying the boundary conditions, then substitute the constants in this equation to obtain the slope and deflection. So the bound constant values are C3 is equal to minus q naught into L cube divided by 24 and C4 is equal to minus q naught L to the power of 4 divided by 120. So upon substituting these values in this equation, then the slope and deflections similar to shear force and bending moment as I explained in the previous slides, the slope and deflections are the equations are given like this. Y is equal to minus q naught x divided by 24L into EA into the bracketed term. Similarly, the deflection y is equal to minus q naught into x square divided by 120L EI into bracketed term. Now, the angle of the rotation and the deflection at the free end of the beam, that is theta b. So the angle and rotation of the deflection at the free end of the beam. So when we discuss about the free end, so that means x is equal to L. So substitute x is equal to L, and upon simplifying, then we'll arrive theta b is equal to q naught into L cube divided by 24 into EI, and delta b is equal to q naught L to the power of 4 divided by 30 into EI. So this is how we calculate the slope and deflection of a cantilever beam subjected to uniformly varying load using a double integration method. Now we'll discuss about moment area method. So in moment area method, there are two theorems, first moment area theorem and second moment area theorem. Now we'll see what is first moment area theorem. In first moment area theorem, the angle theta b upon a between the tangents to the deflection curve at 2 points A and B is equal to the area of the M by EI diagram between those points. In case of second moment area theorem, the tangential T b upon A derivative of point B from the tangent at point A is equal to the first moment of the area of the M by EA diagram between A and B evaluated with respect to point B. Now this is what is a diagram, M by EA diagram. So now for cantilever beam, so this is a moment diagram which is in cubic curve, and this is the value of moment at point A. If you divide this term divided by EI, then we'll obtain M by EI diagram. So this entire diagram is the M by EI diagram. That is Q naught L square divided by 6 EI. And for this cubic curve, the area is B into H divided by 4. So where B is equal to L and H is equal to Q naught into L square divided by 6 EI. And the distances from centroid to point A and point B are given here. That is L by 5 and 4L by 5 respectively. Now, according to the first theorem, the slope at point B is equal to the area of the M by EA diagram. The area of a cubic spandrel is BH by 4, as I discussed in the previous slide. So theta is equal to 1 by 4 into Q naught L square divided by 6 EI into L. So this is what is the area of the cubic curve. So 1/4 of this is what is the B H, and this is L. So that is theta B is equal to Q naught into L cube divided by 24 EI. And the same slope value that we obtained using a double integration method also. Now, deflection is 1 by 4. So for deflection, where you are calculating the deflection is very, very important. That is 1 by 4 into Q naught L square divided by 6 EI into L. So this is what is the area multiply with the centroidal distance. So this 4L by 5, if you see at point A, the deflection value is equal to 0. But whereas at point B, the deflection exists. Now, from the centroidal distance to where you are calculating the deflection is very, very important. So that's why the distance is equal to 4L by 5. So substitute 4L by 5 here, and to obtain theta b. Theta b is equal to Q naught into L to the power of 4 divided by 30 into EI. So this is what is the deflection and the slopes using moment area method. Now let us discuss about the deflection by conjugate beam method. So in case of conjugate beam method, there are two things. One is the real beam, the other one is conjugate beam. So real beam means the beam which is given in the problem, and a conjugate beam is an imaginary beam with some with certain conditions. Suppose in real beam, so if the support is a fixed one, then in conjugate beam it becomes as a free end. Similarly, in real beam, if the support is a free end, then it will become fixed end. And in case of real beam, so whatever the loading that is acting on a beam, if you draw the bending moment diagram, so that bending moment diagram will become the loading onto the conjugate beam. So here in this case, this is a uniformly varying load, and the bending moment diagram is the uh, cubic curve. So this is what is the cubic curve, and the intensity value is Q naught into L square divided by 6 EI. Now, slope is at any point on a real beam, the shear force in a conjugate beam at a corresponding point gives the slope of the real beam. Similarly, the deflection is the bending moment in a conjugate beam at any point corresponds to the deflection of a real beam at that point. So that means theta B is equal to, that is the shear force at point B. So if we calculate the shear force at point B is the 1/4 of Q naught into L square divided by 6 EI into L, which is equal to Q naught L cube divided by 24 EI. Similarly, theta B is equal to the bending moment at point B, that is Q naught L cube divided by 24 EI into 4L by 5, which is equal to Q naught into L to the power of 4 divided by 30 EI. So this is how we calculate the slope and deflection of a cantilever beam using uh, conjugate beam method. Now let us discuss about the deflection by strain energy method. Strain energy method. So we have two theorems. One is Castigliano theorem 1 and Castigliano theorem 2. So we'll discuss what is Castigliano theorems while solving the problem. Here, wherever you are calculating the deflection, so there we assume a fictitious load P. So here in this diagram, you can see the fictitious load P. And the total load to the right of the section X is a triangular load. Load is equal to 1/2 into L minus X into Q naught L into L minus X. So which is equal to Q naught divided by 2L into L minus X whole square. Now, the centroid of this triangular load is located is equal to 1/3 of L minus X from section A. Now, here the total load, whatever the total load that you calculate here, so let us take, so this is what is the triangular load that we consider. So the intensity is Q naught into L minus X divided by L, and the area of this triangular load is equal to half into Q naught into L minus X divided by L into L minus X. So if you consider this is the X distance and this distance is L minus X. So that's why load is equal to Q naught divided by 2L into L minus X whole square. The centroid of this triangular load is located at 1/3 of L minus X. So that means from section A, from section X. So moment is equal to M of X is equal to this distance multiply with 1/3 of L minus X. So then we'll obtain minus Q naught into 6L into L minus X whole cube. Then strain energy stored in a beam is equal to strain energy stored due to the bending. As we know the equation U is equal to integral 0 to L into M of X whole square divided by 2 into EA into dx. Now whatever the moment value that we obtain here, that is a minus Q naught divided by 6L into L minus X whole cube divided by 2EI into dx. So substitute the mx value here, that is u is equal to integral 0 to L 1 divided by 2EI into Q naught divided by 6L into L minus X whole cube. So this entire term you have to take square of that into dx. Except L minus X term, the remaining terms you take out of the integral. So then Q naught square divided by 6L, that is 36 into L square multiply with 2 EI. So then it is 72 EI L square. Integral of 0 to L into L minus X whole to the power of 6 into dx. So consider U is equal to L minus X, and upon integrating and applying the limits of the integration, then U is equal to Q naught square into L to the power of 5 divided by 504 into EI. So apply the Castigliano theorem. So to find out the deflection at point, introduce a fictitious load P at free end in vertically downward directions. Then the moment, so whatever the moment that we calculated, that is M of X, it should be updated. So the updated moment is equal to M of X is equal to minus Q naught divided by 6L into L minus X whole cube plus P into L minus X. So this P is the fictitious load and L minus X is the perpendicular distance. Then the total strain energy is equal to U is equal to integral 0 to L 1 minus 2 EI into the entire moment, updated moment whole square into dx. Now apply the Castigliano theorem. So the Castigliano theorem now apply the Castigliano theorem. That is delta is equal to dou U divided by dou P. So delta is equal to 1 divided by EI into integral of 0 to L and U. So this is what is the entire U term. Um, we are differentiating with respect to P. So remember the differentiation we are considering is the partial differentiation. Now we take the derivative of the above equation and set P is equal to 0. Then the final equation is equal to delta is equal to 1 by EI into integral 0 to L, the momentum into dx. Then we'll obtain minus q naught divided by 6 ei into L integral 0 to L minus x whole to the power of 4 into dx. Then upon integrating and apply the limits of integration, then we'll obtain delta is equal to minus q naught into L to the power of 4 divided by 30 into ei. Now we calculated the deflection. Now we'll discuss about the how to calculate the slope using strain energy method. Similar to the deflection, here we apply the dummy moment MD at the free end because we are going to calculate the slope at free end. So that's why we apply the dummy moment at free end and find out the slope. So the moment is equal to updated moment is equal to minus q naught into 6L into L minus x whole cube plus MD. So this MD is the dummy moment or fictitious moment. Then calculate the total strain energy is equal to U is equal to integral 0 to L M x whole square divided by 2A into dx. So substitute the moment value in this equation, then apply the Castigliano theorem. So now differentiate U with respect to MD to obtain the slope. So that is theta is equal to dou U divided by dou EMD. Theta is equal to 1 by EI into integral of 0 to L minus Q naught divided by 6L into L minus X whole cube plus MD multiply with 1 into dx. Evaluating the integral by considering MD is equal to 0, then we'll obtain theta is equal to minus q naught into 6 ei into L integral 0 to L into L minus x whole cube into dx. So consider in case of deflection, similar to that, we consider U is equal to L minus X and upon integrating and apply the limits of integration, then theta is equal to minus Q naught into 6 EI into L to the power of 4 divided by 4. When you apply the moment, when you apply the limits, then the X term will become 0. Then this theta will become minus q naught into L cube divided by 24 EA. Then the slope at the free end, which is in radians, theta is equal to minus q naught into L cube divided by 24 EA. Now this is how we calculate the slope and deflections using double integration method, moment area method, conjugate beam method and strain energy method. So among all these methods, conjugate beam method and moment area method are little bit easy methods compared to the double integration method and strain energy methods.